Welcome back. So we still have two talks for this session that are somehow industrial related, or at least the speakers were in industry. The first talk will be by Morgan, and it will be about learning the privacy utility trade-off.
Thanks. Can you hear me well? Is this on? Yeah. So I want to first thank, sorry. I want to first thank the organizers for giving me the opportunity to speak here. Anything I'm going to say is about my personal opinion, not that of my employer. And what I'm going to talk about is this joint project with a few people, including Brendan Avent, who's there in the audience, who interned with us last summer. And as the title gives it away, I'm going to talk about the privacy utility trade-off, which is something that probably has come up in every talk we've heard until now. And I'm going to talk about like a very practical take on balancing the privacy utility trade-off. I'm going to talk about the kind of information about the privacy utility trade-off that you need when you are in a team that's developing a product or a service that will be potentially use sensitive data. And for the purpose of this talk, if you're bothered by the utility word, you can think about something much more concrete. You can think about the error rate of a machine learning classifier, for example. So if you're trying to build a product or a service that will have this machine learning part and that will have to deal with potentially sensitive data, usually you might be part of a team that contains scientists and engineers, but ultimately you're going to have to interact with a number of people. You're going to have a number of conversations about utility and about privacy to decide where in the space of the trade-offs you should sit. And when you want to have these conversations, you actually are going to need very precise numbers so that these conversations can be fruitful and you can make informed decisions about whether the system that you currently has can find a point in this trade-off that satisfies the requirements in terms of utility and privacy that you're going to have, or whether you should go and try to improve your system. And there might be many ways to do that. You can try to design better algorithms. You can actually try to run the same algorithm but collect more data. It might be that maybe you're not achieving a good privacy utility trade-off because your privacy analysis is not tight, so you might try to go and get a tighter analysis. Or you should also have enough data to decide that you should give up and abandon this quest. So the question is, how are we going to do this in practice? And I want to start by talking a little bit about the distinction when we talk about the privacy utility trade-off between the theory and the practical point of view. So my background is machine learning theory. So when I initially started working in differential privacy and I was thinking about the privacy utility trade-off, I was thinking about things like this. So we're thinking about bounds that hopefully will give us optimal rates and will depend on the parameters of the problem, like the dimension of the data, the privacy parameters, the amount of records that we have. But even when you have these bounds, and even when we know that they're like optimal in the sense of rates, like these usually don't give you enough information to have the sort of conversations that you need to have when you're trying to put something into production, for example. So things that might happen is that you might not have explicit constants, or you might have explicit constants, but the constants are totally unrealistic, or maybe the bounds are just worst case bounds, but it so happens that in the application or like the particular data set or the particular setting of that you're trying to run your algorithm, maybe this bound is not exactly what it should be. So maybe, I don't know, maybe the D should be a log D in the case that I'm trying to apply the algorithm to. Maybe this 1/n rate only kicks in when n is on the order of millions, and maybe I don't have millions of data points. So in practice, what you want is information closer to this kind of plots that John was showing yesterday, and then I shamelessly borrowed from his presentation at the CSAC meeting in December, where things are way more concrete, right? So here we have like privacy laws with actual numbers, we have accuracy with actual numbers, and this is the kind of information that we need in order to make these decisions and decide in which point we're gonna operate on. Or decide whether there's no point that is good enough for us and we need to go back to the whiteboard and design a new algorithm or collect more data or whatever it is the action we want to take. Now, the one problem arises when you try to get these plots when you're in particularly machine learning applications where you have algorithms. Sorry, this is not connected. When you have algorithms like the differentially private stochastic gradient descent, for example, right? So Ulfer did a great job at introducing machine learning, so I don't have to talk too much about it. But just let me remind you that stochastic gradient descent is one of the basic algorithms that you are going to use in machine learning, even when you don't care about privacy. And this is an algorithm that is going to like iterate over your data set, and at each iteration, we're going to take a small subsample of the whole data set, training data set, and we're going to compute the gradients on the current parameters on this subsample, and we're going to like iterate over that to keep improving the parameters. Now, the problem here is that when we try to privatize this algorithm, we make some changes. So for example, we clip the gradients, we add some Gaussian noise, and so on. So we end up with algorithms that have a relatively high number of hyperparameters, right? For example, in this simple setting, we at least have 5 hyperparameters. We have the learning rate, we have the mini-batch size, number of epochs, noise variance, and clipping norm. And we know, for example, from Vasily et al., that, well, the theory gives us a nice way to tune these hyperparameters to achieve near optimal rates in terms of some notion of utility when the optimization is convex. But in practical applications, these days, people solve a lot of non-convex problems, especially deep learning problems. And in this case, we don't have good utility bounds or utility bounds at all that we can use to decide how we're going to set up these hyperparameters. And note, for example, that here, even if I didn't care about the privacy utility trade-off, even if I just cared about like achieving a fixed level of privacy, things are not as easy as they seem, because there's many ways in which I can like play with the privacy of this algorithm, right? So if, for example, I'm interested in getting more privacy, I can increase the level of noise, I can decrease the size of the mini-batch, I can decrease the clipping norm. So how should I like tune these hyperparameters, even if I just want like a fixed epsilon, I want the best utility? So this is the kind of questions that you need to be able to answer if you want to put these things into production. So what we would really be interested in having are plots like this, which are very much like John's plots, but here in the y-axis I have error instead of accuracy for a small technical reason that is not very important. But basically what we want is to have this sort of Pareto fronts that tell us for a given algorithm or a given model or a given algorithm and a model what is the best accuracy that we can get for a given epsilon, and then ideally like click on here and see what are the hyperparameters that give you this sort of trade-off. And what we would like to do is be able to compute these plots relatively efficiently. And this is one of the problems with machine learning. So to get just one point in here, you might need to train one or more machine learning models. And when you're talking about deep learning models, this can take hours or even days, depending on the size of your training data sets. So we really want to like be able to do this in a reasonable time. So not evaluate the algorithm on like a grid search over all possible hyperparameters. We also want to be able to do this using measurements of utility that are empirical, right? Because in many cases, we're not going to have bounds to get the utility. And finally, what we would like to be able to do with these plots is to enable fine-grained comparisons. Like, for example, in this experiment that we did, we took the MNIST data set and we tried two multi-layer perceptrons. So they're neural networks, they're not very deep. But we tried two architectures, and we're trying to see whether one architecture is better than the other in terms of achieving a good privacy utility trade-off. And we wanted to do that in reasonable time.
Before you leave it, so the only reason that I do it the other way is just one minus two classification, right? Is because then the economists recognize it. Is it really non-convex in that region, the gold one?
Sorry, come again?
So that Pareto frontier ought to be convex. Is it really not convex there?
No, it doesn't need to be convex.
Between some point on the gold one and some other point on the gold one that's outside the Pareto frontier, I don't believe that.
I'll show you another illustration in a minute of how we build this Pareto front that I think is going to answer your question. But the Pareto front doesn't need to be convex, I think. It's just like...
It's not a Pareto frontier if it's not convex, but that's okay. But it's just...
Okay.
Well, it's a large.
Well, they're using some sort of empirical done.
When I see that in one of these applications, I assume the algorithm messed up in the region where it's not convex.
It can be.
Okay. Well, we'll see when I explain how we do that.
Do you want to do that in a privacy-preserving manner, or you don't care about that?
I'll have a slide about this at the end. Yeah. So for now, what I'm going to assume is that I have a utility or error oracle. And I'm not going to try to specify where this comes from right now, and then we'll talk a little bit about it. And yeah, there's going to be some sort of problem depending on how you measure the error. Yes. So just to abstract a little bit what we're trying to do, we formalize introducing parameterized class of algorithms. So these are all the algorithm configurations that we're going to try, and lambda is the configuration in some hyperparameter space. And we assume that when we choose a setting for the hyperparameters, we can evaluate the error, and it's going to be a number between 0 and 1. So we have this error oracle. And we also have a privacy oracle that might return a number between 0 and infinity. And you can think, for example, that this is epsilon for some fixed delta, but you could also have other things in there. Okay, so given these objects, what we're really trying to do is we have some hyperparameter space that might be high dimensional, might be a bit complicated in its geometry. And we have this two-dimensional plane of error versus privacy loss. And what we're going to do is we're going to successively pick hyperparameters that might seem interesting to us, evaluate the error and the privacy loss using the oracles. And that will give us a point in that plane, and we can repeat this over and over again. And at some point, we get all these points, and we would like to build a Pareto front that tells us that based on the information we have seen so far, these are kind of the best configurations, right? So the best configurations will come, and I hope this clarifies your question, by picking the set of non-dominated points, which are the points where we cannot improve, say, we cannot decrease error without increasing privacy, or the other way around, and joining them by lines. So I don't see why it should be convex from this picture.
It's from the basic economics. It basically means you didn't explore the parameter space in sufficient granularity to find the point between your yellow and your green dots there that dominates your red one.
But I don't know, it could be that it's like this, right?
But
Then it wouldn't be convex.
it's perfectly okay if that's the best you can do. And that's a production possibility frontier, but it's not a Pareto frontier because...
Okay, so let's call this an empirical Pareto frontier.
In principle, you should be able to get to this is why it's easier to draw them this way, to get to a point that's closer to the origin, in your case, by combining the algorithms that gave you, in this case, the green and the yellow one.
It's not clear that there's the convexity, that like linear combination property makes sense. For one thing, also it depends on the scale of the x-axis, right? If it's on a log scale or something, like there's some implicit linearity
labeling
assumption.
it the Pareto frontier and not with saying that this is an empirical method for determining feasible combinations.
Okay. So the point here is that this hyperparameter space is huge. So there's a lot of other settings that we could try that are not going to give us Pareto-optimal points. So in trying to determine this empirical Pareto frontier, what we would like is to somehow efficiently explore the hyperparameter space to find points that are close to the true Pareto front and ignore all the rest.
So that's the right way to define the exercise. And when you find non-convexities in that Pareto frontier, it suggests that the exploration algorithm was insufficiently granular. That's what I'm trying to say.
It needs to be monotone. It doesn't need to be convex. Because it's not because again these are two parameters. It very much depends on the space of parameters. And some space of parameters, like changing the parameters might not actually improve your utility. And vice versa. For example, mixing two algorithms with two different epsilons only maybe improves epsilon by just a tiny bit. Like you cannot just mix. Like some parameters are. Some measures of performance will.
Yeah, I think that's true when the two objectives are added up, that you get convex region. But in here, we're not adding them up.
Is either minimize the error for a given privacy loss or minimize the privacy loss for a given error. Now, the solution to one of those two optimization problems describes a frontier, which is usually convex. If this one's not convex, I would like to see the proof.
I think it's convex, yeah, when you sum the two objectives, but not... Well, we can take this offline. So what we're going to do to do that is use Bayesian optimization. So Bayesian optimization is kind of a well-established technique for optimizing black box functions that are expensive to evaluate. So it's a whole field of study. And I'm just going to give you like the nutshell introduction. And I should also mention that it's something that is widely used in applications, not only for hyperparameter optimization in machine learning systems, but also in many other places like scheduling and planning, for example, for airplanes, when you have like very expensive simulations to evaluate each experiment, experimental design in chemistry and biology, and so on. So the way the typical way Bayesian optimization is formalized when you have at least like one objective is that you're given a function defined on some subset of p-dimensional Euclidean space. You assume that this function is expansive, non-convex, and has some degree of regularity. And what you want to do is try to find this by just doing evaluations, like try to find this minimum by just doing evaluations of f. So you don't have gradients, for example. And the way a Bayesian optimization loop works is the following. So we keep track of k evaluations of the function on lambda 1, lambda k points. And using this data, we build a surrogate model for f, right? So, for example, typical Bayesian optimization would use a Gaussian process for that. And if you don't know what a Gaussian process is, don't worry. Just think that what we're doing is we have these few evaluations of f, and we're doing some interpolation in the hyperparameter space. And this interpolation is probabilistic in the sense that it doesn't only give us like some shape f hat for f, but also gives us some degrees of uncertainty around this interpolation. And using these degrees of uncertainty and the means, we will try to find the most promising next evaluation, which typically involves like solving an exploration-exploitation dilemma, because so we're going to have regions where we haven't collected any information, because this hyperparameter space might be really big. And in that case, we might, there's a potential that the minimum that we're looking at, that we're trying to find, is in that region that we haven't explored. And we should probably explore a little bit more. But also when we have indication that the minimum can be around some place, so we have a place where this f hat is relatively low, we might want to do some exploitation and try to do some local search around that area to see if we can improve that minimum a little bit. So if that didn't make any sense to you, let's do it again through an example. So this is a one-dimensional example of Bayesian optimization. And the goal here is to minimize this green dotted line, right? That is this objective function f that we don't know. We just have access to it through evaluation. And we want to find the minimum, which is going to be here. And you don't see that? Ah, well, you can see there in those other screens. Sorry? Yeah. So so here we just evaluated the function at least in one point. And we have the surrogate model that is this black line that says, well, I just know that the function here at 0.5 has this value, so I'm going to think maybe it's just like flat. But there's some uncertainty around this flatness, which you can see in the other screens. And using this mean and this level of uncertainty, we can derive what's called an acquisition function. And the acquisition function, in this case, is just the expected improvement, tells me for each point that I could pick next, what is the expected improvement in the minimum that I can, or expected improvement in information about the minimum that I can get by picking a point. So in this case, there's this red line here that says, well, this is the maximum of the acquisition function, so you should sample this point. So that's what the Bayesian optimization loop is going to do, is going to sample the function on that point, and since that is actually larger than the point that we had here. And using these 2 points now, we have a new model, and we have a new uncertainty, where you see that around the point that we have sampled already, there's no uncertainty left. Although, if you just can sample with noise, you can also incorporate that into your model. And now we're going to have, using the new model, a new acquisition function. Now it's going to decide to sample on the other extreme of the interval. So when you iterate this a couple of times, you keep reducing the uncertainty about your function. Your kind of average function, the black line, keeps getting closer and closer to the green one. And the points that the acquisition function tells you to sample start to concentrate around the minimum. So here, for example, in 9 evaluations, we've basically identified the minimum. So that's Bayesian optimization in one dimension. And we can do all that with just evaluating the function in points. So we are optimizing without computing gradients.
Will you say more about the acquisition function?
That we use?
Yeah, telling you where to sample?
A little bit, yes, a little bit about the one that we use. You mean? Yeah.
Do you have a prior? Is it a uniform prior?
I'm sorry.
A prior, so in this type of models, there's a prior about the function that we're trying to optimize. And the prior is encoded in terms of a kernel that helps you define the Gaussian process. And this is where the smoothness assumption comes from. So you encode smoothness assumptions or other sorts of assumptions in the kernel of the Gaussian process. And I mean, it's important that you have at least some assumption, because if the function was totally wild, how am I ever going to pick the minimum, find the minimum with anything reasonable if there's no smoothness? So the algorithm that we designed to find these Pareto fronts, we call it DPareto. So it's in this case, it's a multi-objective Bayesian optimization, because we're trying to minimize 2 objectives at the same time. We're trying to minimize the error and minimize the privacy loss, and that's why we put error instead of accuracy, because then we are minimizing both, and if we try to minimize one and maximize the other, it's just...
Just subtract.
Yes, yeah. So in this case, obviously, there's no minimum. There's just a Pareto front of minimums. And the algorithm basically implements this Bayesian optimization loop very simply. So we're given the hyperparameter set. We're given the privacy and the error oracle. We just start by picking some fixed number k0 of random samples, so we can bootstrap these models. So these are just random points at which we evaluate the privacy and the error oracle. and we keep building a data set by adding all the points that we've observed so far. So once we've bootstrapped the model, we are going to do k iterations, and this is the budget of how many times you're willing to evaluate your privacy and error oracles that might involve training machine learning model.
I figured out why I don't like this. If you want to take the question, strategy space. You're saying that the only things that could be on the Pareto frontier, IER, are the points that your search algorithm found. But in fact, you can randomize between any two of those points, and that's also an available strategy, and that's why you should get a convex Pareto frontier.
But I don't see why, for example, interpolating, not taking the average of two hyperparameters is going to give me the average utility or average privacy.
From two different runs, randomly. That's the right way to think about it. You're not constrained to use only one. You're constrained to get the minimum error given a privacy loss. You don't know which one ex ante.
Right, but if you... The privacy parameter is going to be the worst between the two.
Yeah, the privacy
parameter is not going to be the average, it's going to be the weighted average.
It's almost
going to be the worst between
it'll be almost the worst one.
Yeah, it could be the worst.
All right.
Okay.
I'm very sympathetic to this exercise. That's why I can't figure out why you don't think the Pareto frontier should be convex. But I'll take it all offline.
Okay, so and in this case, when you're doing multiple objectives, like acquisition functions get slightly trickier, which was Cynthia's question. So in this particular case, we're using a hypervolume-based probability of improvement, which is an acquisition function that tries to do the following. So if so far I've found a Pareto front like this, so for each potential new hyperparameter setting that I can try, my Gaussian process models will allow me to predict where more or less this is going to fall in the error privacy loss space. So the improvement then that you get on the Pareto front, you can somehow measure it by the volume that you're adding to your Pareto frontier. So this type of acquisition functions, and there are several variations of this type of acquisition functions for Pareto frontiers, will try to find the next hyperparameter point that will give you the maximum improvement in terms of the volume that you're adding to your Pareto frontier. So let's see an example where the Pareto front is not convex again. Sorry. So we wanted to have probably something that's kind of the simplest example where we can illustrate what's going on. So we modified the sparse vector technique a little bit. So it just has two hyperparameters. So here we have a sparse vector technique that's going to take a data set Z. Is more of a batch type SVT. So we're going to receive M queries. And what we're going to do is, for each query, we're going to evaluate it on the data set. We're going to add some Laplace noise. We're going to compare it to a noisy threshold. And we keep a vector W that is initially all zeros. And we're just trying to find which of the queries are going to return 1. So here we're just taking 0, 1 valued queries. And something that's slightly different from the way you usually see sparse vector technique is that here, instead of the hyperparameter being epsilon, we have hyperparameters, the amount of noise and a bound on the number of ones that we're willing to put in here, and then we split this noise like using some formula that is in this understanding SVT paper to minimize the variance. And of course, using in terms of B and the number of things that we're willing to answer, there's a formula that gives you the resulting epsilon. And what we want to do here is basically evaluate what settings of these hyperparameters lead to optimal privacy utility, an optimal privacy utility trade-off. So the experiment that we set up, we set M to 100. There's 100 sensitivity 1 queries. And we select, so we randomly make it so that 10% of them have answer 1, and the others have answer 0. So the privacy oracle here is just a closed formula. And the error that we're going to evaluate is 1 minus the F-score, which is the harmonic mean of precision and recall in terms of finding which queries return 1. So this is not the standard notion of error that people have looked at when analyzing the utility of the sparse vector technique, but it's a nice, cute little number that gives you an idea of how good you're recovering which queries give you 1. So if you do that, because here we only have 2 hyperparameters, we can do an exhaustive search by taking a very fine grid on parameter B and on parameter C and see what epsilons are you getting and what is the error that you're getting. And here, obviously, the error needs to be evaluated empirically. So we take an average over 50 runs. And using this information, you can compute the Pareto front more or less in closed form. And you get this Pareto frontier here. And here you can see what the inputs that lead to different points by matching the colors across the 2 plots. So now that we have this information, which is kind of like the almost exact Pareto frontier for this algorithm, we can try to see what the Pareto does in this case. So here I'm showing you so what happens when we initialize with 250 randomly sampled points. So these maps here are the results of the Gaussian process trained on this random sample data, which starting to look very much like the true error and privacy oracles. And using these 250 sample points, we recover this empirical Pareto front, that is the black line here, based on these blue points in the error privacy space. And we see that it's starting to look very much like the true Pareto frontier. And on top of that, we can now use these Gaussian processes to plot the acquisition function and see where the Pareto thinks that it should sample next. And I don't know if you can see that, but there's 2 regions here that are relatively empty in terms of the random sampling, and that could potentially give us points in the Pareto front. So the point here, we're not going to get much in the Pareto front. So the model has learned that, and we have like a region here where it would be interesting to sample, and there's another region here that I don't know if you can see in these plots. But well, the point is that the acquisition function decides to sample here, which is actually a point that is trying to close this gap here in the Pareto front. So it's kind of doing what it's supposed to be doing. So now a remark to address with Kobe's question was about whether the oracles might leak privacy or the Pareto front might leak privacy. So when you're trying to do this in practice, you're going to have to make like a lot of this implementation decisions. For a privacy oracle, for example, you can try to like get epsilon for fixed delta. You could also try to use other variants of differential privacy. You could even consider some other attacks like membership inference attacks or reconstruction attacks and put the success metric as your privacy oracle in there. On top of that, you might have whichever thing you pick in here, you might have it available in closed form, or you might have to do some numerical calculation like the moments accountant, and that's what we're going to do next in some machine learning experiments. In terms of the error oracle, you can also think of a lot of alternative definitions. So you could think, what is the error for a fixed input? You could think what is the error for a distribution over inputs, or worst case over a set of inputs. You can also try to have error on expectation with high probability. And it would be really nice if you had the exact expressions for the error oracle, but that's, I think that's very unlikely in most cases. So you can rely on empirical evaluations. So these are the choices that we make in our machine learning experiments. And indeed, because we are evaluating the error oracle on a fixed input, which means that, in this case means that we're training on a fixed data set and then we're reporting the error on a holdout set, but that we're going to reuse every time we call the error oracle. And we do like several repetitions because there's randomness introduced by differential privacy. The values returned by the error oracle might be leaking some privacy. So we didn't try to address this explicitly yet. There's several solutions you can come up with from the solution 0, which is let's ignore that issue. You could try to perform this privacy utility exploration on a public data set that is already released and that you know that is kind of like follows a similar distribution to the one that you want to train your data on, which is the Pate type approach. Or you could privatize the evaluations of the error oracle, but then you will have to make peace with the fact that your Pareto front has additional sources of noise, so your decisions might be less reliable, let's say. So in terms of machine learning experiments, we work with two data sets, the adult data set and the MNIST data set. And we tried a couple of things. So for the adult data set, we tried logistic regression with two different optimizers, linear SVM with an SGD optimizer. And we recovered these Pareto fronts here that, although obviously they're noisy, they're based on 16 bootstrap points of random sampling plus 256 iterations of the Bayesian optimization loop. We're starting to see interesting things, like, for example, it seems like SVM is not that good in this regime of epsilons as, for example, logistic regression. And, for example, Adam might be doing a better job in the high privacy regime at finding, well, at not like blowing up the accuracy immediately when you go to that regime. For the MNIST data set, we tried just stochastic gradient descent on two different architectures, deep learning architectures. They're not very deep, so one just is a multi-layer perceptron with one hidden layer with 1,000 units, and the other has two hidden layers, one with 128 units and the other 64. And this is the plot that I showed you at the beginning, which seems to say that, well, if you are in the high privacy regime, epsilon more than 1, both architectures seem to be doing the same. But as you move closer to, say, epsilon 0.1, the architecture that has less hidden units is actually doing better than the architecture that might be too big for this problem. The other type of experiments that we did are about making sure that this makes sense in the sense of comparing the Pareto, so the Bayesian optimization, against some simple baseline strategy, which is random sampling. So what happens if instead of trying to do this very fancy thing of picking the points using an acquisition function based on Gaussian processes trained on the points we've seen so far, we just go and do some random sampling. Obviously, random sampling is quite good. It's eventually going to find very good Pareto fronts, but it's going to take you many, many more evaluations, right? So here there's three different things to see this same phenomenon. So here, for example, in the case of logistic regression with SGD, we have the Pareto front learned by DPareto with 256 iterations of the Bayesian optimization loop versus 1,500 random sampled points. And the two Pareto fronts start to look very much when you have this difference in the order of magnitude. But it's interesting to see that DPareto is always trying to sample things that are very close to the Pareto front, whereas random sampling is a little bit all over the place. So these Gaussian processes are learning what they're supposed to be learning. Another way to see the same phenomenon is here, for example, where in this MLP2 model, here we have the Pareto front that we obtained with these 16 initial random samples. And then we can add the same number of additional points either via random sampling sampling that gives you this Pareto front, or with Bayesian optimization that does a much better job at finding how you tune the hyperparameters to move into the low privacy regime. And the third plot is kind of illustrating the same with another type of measure, a measure of how the hypervolume improves as you increase the number of points, either with random sampling or Bayesian optimization. Okay, so I'm just getting to the conclusion. I think that empirical privacy utility trade-off evaluations are very important to enable application-specific decisions, like this idea of how you, for example, should choose an architecture for machine learning or an optimizer if you want to balance the privacy utility trade-off. And our results show that Bayesian optimization seems to provide a computationally efficient method, at least when you compare it to random sampling, to recover this Pareto front. And this is especially useful when your hyperparameter space is very large. And here, 5 hyperparameters is already quite large, right? Because this, like, the size of a potential grid search would grow exponentially with the number of hyperparameters. So in future work, we would like to see what is the best way to address the leakage in these Pareto fronts coming from the error oracle when it's evaluated on specific inputs. And we'd also like to explore other things like introducing further criteria in the optimization, for example, running time. So you might have additional trade-offs between running time, accuracy, and privacy, and this kind of framework allows you to also introduce other criteria. So if you have any other criteria that you think would be interesting to explore here, I would love to hear about it. And that's all. Thanks.
Well, I was going to give others a chance.
Maybe not about complexity.
Can you just put up the one that we've been arguing about, discussing?
This one?
Yeah. Is that actual data when it goes from 1.0 to 0.85 or so? The first chunk of your goal.
This chunk?
Yeah.
No. So here.
Evaluations that.
No. So here I'm just signaling that I never saw.
So that's why it might be more productive for you to draw it the other way. So the economics of this is that if that is actually the Pareto frontier, starting with the first real point, not with the 0, 1 point, but the first actual point that you got, then what it means is that the technology you're trying to implement has a region of increasing returns in epsilon. And so that means the decision problem that you're implicitly posing here is not going to be well behaved, because if I map my preferences over error and epsilon, and they have classic preference characteristics, there's going to be 2 or more points that intersect with the Pareto frontier instead of being tangent with the Pareto frontier. So there'll be interesting situations where I might take a massive amount of inaccuracy because I took a very, very small epsilon, or a much larger, more accurate epsilon that a preference indifferent. And that's allowable when there's this increasing returns to scale. Those things usually cause the real decision problem, which is this is the choice set, but my preferences come from other things, from a social welfare function, to get very difficult to give a good answer to. What we have found, we adopt the strategy that we try to use public data for the evaluation, but the ones that you drew a picture of, for example, you stole from one of my presentations, that was public data, but I didn't do them. My team did them. As you increase epsilon, all of these well-implemented algorithms get you back to the truth. So there's a region of what's decreasing returns to scale in economics terms, which is what gives you the convexity of the Pareto frontier, that is built into any algorithm that has the property that when you give it an infinite privacy loss budget, you get back the truth.
Okay, yeah, so...
That's why I said that it should be convex, because it eventually has to be convex. But I was I thought that that region of non-convexity that you had there was due to actually having evaluations that were between the 0.85 and 1. But that's just, you just drew that line in. That's not the first real evaluation is some epsilon.
Is this one here? Yeah.
Between the 0.4,
Well,
like the 0.5 and the 0.6.
when he hadn't completed it, he was doing it by example, that it wasn't clear where the increasing returns to scale region was, but now it's clear. You'll probably be able to smooth that out. This procedure has a region of increasing returns, which makes the decision problem about epsilon and accuracy much more difficult because standard preferences will give you multiple solutions. There's a whole literature in economics about
I'm not familiar with that literature. Yeah.
things like that happen when you have these kinds of technologies. And that's interesting in and of itself. But so that's why I was trying to understand why you were showing the non-convex portion of the Pareto frontier. This is only half the choice problem. The other half of the choice problem is you have to express your preferences over epsilon in the classification area, which is not covered by.
No, and we're not trying to cover like that's that's a policy or a business question.
Okay, so let's thank Borja. Our last talk for this session is by Dipesh.